All right, this video we are going to cover chemolithotrophy. So just as a refresher, what we have been doing so far is learning about chemoorganotrophs. So chemoorganotrophs are organisms that get their energy and their electrons from organic chemicals. This is things like us and E. coli. And so, as you guys will remember, the first three catabolic steps, glycolysis, pyruvate oxidation, and the Krebs cycle, are what are responsible for the complete oxidation of the organic carbon compound. And so it is in these three steps that every single one of the carbon-carbon of the carbon-carbon bonds are broken, and then the electrons that are released are picked up by the electron carriers, primarily NAD plus going to NADH and FAD going to FADH2. And then in electron transport, we're going to use those electrons as they go down the electron transport chain to generate a PMF, and then use that PMF to produce lots of ATP through oxidative phosphorylation. So that's chemoorganotrophs. All of that whole process is powered by the oxidation of an organic carbon compound. Okay, so in this video, we are going to learn more about chemolithotrophs. So chemolithotrophs also get their energy from chemicals, big E for energy, but they get their electrons from inorganic compounds. So litho means rocks. And so chemolithotrophs get their energy and electrons from inorganic compounds. And so these first three steps do not happen in chemolithotrophs. We are going to go straight to electron transport and oxidative phosphorylation. So this is a diagram from your text, which basically summarizes what I just said. And so in chemolithotrophs, we only have electron transport. And so the electrons are going directly from an inorganic carbon compound like sulfur or sulfate or nitrate or nitrite or iron or something, to a final electron acceptor by means of an electron transport chain. And so it is going to be still true that electrons will move from things with a negative E0 prime or negative reduction potential to things with a positive reduction potential, because negative means more likely to donate and positive reduction potential is more likely to accept, right? So reduction is gaining electrons. And so if it is more positive, it is more likely to gain electrons. If it is more negative, it is less likely to gain electrons, and thus more likely to donate electrons, because that is the only other option. So in chemolithotrophs, the electrons are donated from inorganic compounds to a final electron acceptor. That final electron acceptor will also be an inorganic compound. It may be oxygen, as here, or it may not be oxygen, but it's never going to be something organic. Both the electron donor and the electron acceptor will be inorganic compounds. Since we are still powering ATP production from oxidation of an initial compound, we are still going to be making ATP by oxphos, which is going to be powered by PMF, done with the enzyme ATP synthase, and happening in the cell membrane, because all electron transport chains happen in membranes, and in bacteria, the only membrane that they have to work with is the plasma or cell membrane. Okay, and so this is just a list of possible electron donors and electron acceptors. In general, all that you're going to need to know is that both the donor and acceptor are inorganic carbon compounds. I may want you to interpret a chart or even kind of make a guesstimation given values. So I might not give you the chart one time. I might give you just the electron is moving from sulfate to nitrate, from -1 to +4, plus 0.4. Like, how will that compare if the electron moves from sulfate to oxygen or something? So you need to be comfortable using this chart. You also need to be comfortable knowing that things with a negative reduction potential are electron donors, and things with a positive reduction potential are electron acceptors. The more positive the reduction potential, the better an electron acceptor something will be. So this just shows you a little short electron transport chain, and so the electron is being donated from nitrite, producing nitrate, and then it's going to go through this Wiensy electron transport chain to oxygen, reducing oxygen, forming water, and then in the process, some protons will be pumped out to help generate a PMF. This is a cytochrome, and so you may remember that cytochromes contain iron and can help in the electron transport chain. Okay, hopefully this is good so far. The thing that is a little bit weird with chemolithotropes is that they are starting with inorganic carbon, not inorganic carbon, that makes no sense. They're starting with inorganic compounds as the electron donor. And if you look at this chart, which is different than the one we've seen before, but still, so this is inorganic, reading down the list, and then these are inorganic here. So you can see on this chart, there is only one inorganic thing that will be able to donate electrons to NADPH, right? So things that are more negative are donors, and so in order to donate, you have to be higher up on the chart. And so you may remember that bacteria will use NADH for catabolic electrons, but NADPH for anabolic electrons. And so these cells are in a pickle because they are going to need to make stuff, and they cannot easily produce this NADPH for to be an anabolic electron donor if they are starting with some inorganic compound that already has a more positive reduction potential than the NADPH. So that is the biggest problem for chemolithotropes, is how to generate NADPH. Okay, 1 second, I need to fold this over before you see it. Okay, so what they do is they actually have a two-pronged electron transport system. And so just ignore this. Here we go. And so this is the little electron transport we looked at before, like one slide ago, that has the nitrate going to the nitrite, the electron going to the oxygen, some PMF generated. This is electron transport going from more positive reduction potential, oh crisis, I've got that backwards, more negative reduction potential to more positive reduction potential. Okay, so the electrons prefer to move from negative reduction potential to positive. So this is what we have been calling regular electron transport, but which now we will call forward electron transport, because it goes in an energetically favorable direction and thus does not require input of energy. In fact, this energetically favorable electron transport from better donators to better acceptors creates a PMF. So it makes energy, releases energy. Okay, but remember, the chemolithotropes need to still be able to make some NADPH, which is here on this chart, and so it has a more negative reduction potential than a lot of the things that might be electron donors. And so to make the NADPH, the cell actually does what is called reverse electron flow, which is, so this is your reduction potential chart down here. So this is negative E naught prime, positive E naught prime. So these are donors and these are acceptors, right? So positive, or not positive, forward, sorry, electron transport is like this. And so this releases energy often as PMF. To do reverse electron transport, the electron has to move back up, which uses energy to make it happen. And so chemolithotrophs actually will run some forward electron transport to create a PMF, and then in addition to using that PMF potentially for making ATP or for swimming, they may now alternatively use the PMF to power reverse electron flow in order to make NADPH. So to send the electrons from like nitrate or sulfate or something back up to NADPH requires energy. That energy is provided by PMF, and this, since it goes in an energetically unfavorable direction, is called reverse electron flow or reverse electron transport. This is pretty much the same thing that I just said. So there you have it. So that's chemolithotrophs, inorganic electron donors and acceptors. They have a forward electron transport, which makes PMF, but they also need to do a reverse electron transport, which uses PMF and makes NADPH.